All right, let's dive into a really big one today. It's a puzzle that gets right to the heart of how we understand reality itself. We're going to ask a really provocative question. What if the physicists got the arrow of time completely wrong?
I mean, think about it. This is probably the most fundamental experience you have. You know what you did yesterday, you remember breakfast this morning, but you have absolutely no idea what's for dinner tomorrow. It's a one-way street, right? An egg cracks, it never uncracks. Physicists call this the arrow of time, but the real mystery is, where does it actually come from?
So to figure that out, you first have to know what the standard answer is. You know, the view from the physics establishment. This is the consensus that has been taught by some of the greatest minds in the field for decades.
Okay, so here's the core idea. The fundamental laws that govern our universe, things like gravity, electromagnetism, all the big ones, they just don't care about the direction of time. You could run a film of a planet orbiting the sun forwards or backwards, and according to the laws of physics, both ways are perfectly valid. The laws themselves don't have a built-in forward button.
So if that's true, if the laws are perfectly symmetrical, then this one-way street we all experience can't be a fundamental part of reality. The official line is that it must be something else, an emergent property. It's something that just kind of happens because of the specific way our universe started out. You know, low entropy at the Big Bang. But it's not baked into the laws themselves.
So, to sum it all up, the mainstream view is that time's arrow is basically an illusion, a trick of our perspective. It's not really fundamental. And that's that, case closed, right? Well, not so fast. Because, it turns out, there's a really powerful and, honestly, a surprisingly simple objection to this whole way of thinking. The source material we're diving into today throws down a direct challenge to that decades-old consensus. That's it. No beating around the bush. The source we're looking at says that those famous statements from all those brilliant physicists are just plain wrong. It argues the arrow of time isn't missing from physics at all. So you got to be asking, how is that even possible? Well, the whole argument, the whole bombshell, really hinges on one single mathematical tool that's used absolutely everywhere in physics. It's called the time derivative, and according to this argument, it's the smoking gun. Now, what on earth is a time derivative? I know it sounds super technical, but the idea is actually pretty simple. It's just the tool physicists use to calculate how fast something is changing. Think about the speed of your car. That's the change in position over time. Or a cup of coffee getting cold. That's the change in temperature over time. You can't do physics without it. It's everywhere.
And this, right here, is the crucial part. How do you actually calculate it? Well, you have to take a measurement at a later time. Then you subtract the measurement you took at an earlier time. The entire calculation, the very definition of this thing, depends on you knowing the difference between later and earlier.
And there it is. That's the whole argument in a nutshell. You literally cannot calculate a rate of change. You can't use a time derivative without first assuming that time has a direction. You have to know which measurement came first. The arrow of time isn't something that comes out of the physics. It has to be put in before you can even start.
So let's just lay it all out side by side. The mainstream view says the laws have no direction, but our source's argument is that the math you need to even write down and use those laws absolutely does have a direction built into it. So even if the concept is time symmetric, the language of math we use to describe it isn't. It forces us to pick a direction.
So, what this argument is really saying is that physicists have been on this grand hunt for the arrow of time, looking for it in cosmology and thermodynamics, when it was right there under their noses the whole time. It was embedded in the most basic math they use every single day. It wasn't missing at all. It was just so fundamental, so obvious, that nobody even noticed it. And that, I think, leaves us with the really mind-bending final thought. If something as fundamental as the arrow of time could be hiding, not in some grand, complex theory, but in the simple mathematical tools we use, well, it just makes you wonder, doesn't it? What other huge truths about our universe are sitting right there, hiding in plain sight?